So greetings everybody, welcome to our third example in power series expansions of functions. So what we're asked to do in this case is to estimate the square root of 5 using a second degree Taylor polynomial with the square root of x and have that expansion centered at x equal to 4. So for that we need some derivatives of our function. So starting off there, if we begin with f of x equal to the square root of x, then if we start looking at derivatives, so we have a 1/2 x to the negative 1/2. For our second derivative, we're going to have a 1/2 times a negative 1/2 times an x to the negative 3/2. Then for the third derivative, we're going to have a 1/2 times a negative 1/2 times a negative 3/2 x to the negative 5/2. So if we do a couple of more, so if we have the fourth derivative, we have a 1/2 times a minus 1/2 times a minus 3/2 times a minus 5/2 times x to the negative 7/2. And maybe just one more. So if we look at the fifth derivative, we have a 1/2 times a minus 1/2 times a minus 3/2 times a minus 5/2 times a minus 7/2 times x to the negative 9/2. Now, all of this is really to establish a pattern for what we want to have for the nth derivative. Now, is this really necessary in this particular case? Not really, but it has a larger implication when we start looking at error bounds. So for our kind of general pattern in our derivative, what we're seeing is that in our expansion, we have a power of 2 for every order of derivative that we're taking. And so in our kind of general pattern, we know we're going to have a 2 to the n power. Then what about these alternating signs? Well, the alternating signs we see we have a plus, we have a minus, we have a minus, we have a minus, and a minus. So we have n minus 1 minus signs for the order that we're actually taking the derivative. So that's going to give us a minus 1 to the n minus 1 power. And then finally, for the coefficients, so for our numerators, we see that we have this pattern of 1 times 3 times 5 times 7, and then where will that pattern necessarily end? Well, it's going to end when we have a 2n minus 3 up to that value. And then finally, for our x power, we have x to the negative 2n minus 1 over 2 power. So this kind of gives us a general form for what our nth derivative is going to be. Now if we look at those derivatives evaluated at our point of interest, in particular x equal to 4, let's see what pattern we get from that. So for our original function, evaluated at 4, that was really just the square root of 4, and so we have 2. For our first derivative, at 4, we had a 1/2 times a 1 over the square root of 4, so we ended up with a 1/4. For all of the higher powers, so if we kind of continued that, if we look at the nth derivative, so the pattern that we came up with the nth derivative, we had a minus 1 to the n minus 1, we had a 2 to the n power, then we had 1 times 3 times 5 times 7, all the way up to a 2n minus 3. And then we had, when we evaluate at 4, so in particular, if we put in our value of 4, now we have a 4 to the negative 2n minus 1 over 2. But for that, we can simplify. minus 1 to the n minus 1 over 2 to the n, 1 times 3 times 5, all the way up to 2n minus 3. And so we have a square root of 4, so we have a 2 to the negative 2n minus 1 power. Well, we can bring that to the denominator and simplify that. So we have a 2 to the n power times a 2 to the 2n minus 1 power times a 1, 3, 5, 7, all the way up to 2n minus 3. So this gives us kind of a final value for our derivative at that point of minus 1 to the n minus 1, 1 times 3 times 5, all the way up to 2n minus 3. And in the denominator, we have a 2 to the 3n minus 1 power. So this one will actually work. So this formula will work for n greater than or equal to 2. This gives us that value. Let's see if we can clean that up just a little bit. So this formula will work for n greater than or equal to 2. So we have our value for n equal to 1, and then we have our value for n equal to 0. So if we kind of put this into our Taylor series expansion, what we find then is that our square root of x is going to be equal to our first term, 2, and then our second term of plus 1/4 times x minus 4. And then for all of the other terms, we have our pattern n equal to 2 up to infinity of minus 1 to the n minus 1. We have a 2 to the 3n minus 1. We have our n factorial from our Taylor series expansion. And then we have x minus 4 raised to the n power. Oh, whoops, we forgot our terms. Our 1 times 3 times 5, all the way up to 2n minus 3. And then we have our x minus 4 to the n power. So this kind of shows what our full Taylor series expansion is going to look like. Now the implication for this, when we start talking about convergence, for what values will this series actually converge for? For that, we look at the ratio test. So going back to the ratio test, we look at the limit as n goes off to infinity of the absolute value of a sub n plus 1 over a sub n. And so in this case, what it comes out to be is, if we plug in our n plus first value, so minus 1 to the n, times 1 times 3 times 5, all the way up to what I get when I put in n plus 1 into that. So I have a 2 minus 2n minus 1, all of that over 2 to the, I put in an n plus 1, so that's going to give me a 3n plus 2. I have an n plus 1 factorial, and then I have an x minus 4 raised to the n plus first power. Okay. Then what do I have? I have the reciprocal of my nth term. So that reciprocal of my nth term is going to give me a 2 to the 3n minus 1 times n factorial on top. And then on the bottom, I'll have a minus 1 to the n minus 1, 1 times 3 times 5, all the way up to 2n minus 3. And then I have my x minus 4 raised to the n power. So now comes a lot of simplification from that. So I look at my limit as n goes off to infinity, and lots of things will cancel. So what I see canceling there is my n factorial cancels with my n factorial in the denominator. My 2 to the 3n's, So my 2 to the 3 n's will cancel. My minus 1 to the n's will cancel, but they will also get killed off by the absolute value. My x minus 4 to the n powers get canceled. My 1 times 3 times 5 all the way up to, so the term preceding this one, so the term preceding my 2n minus 1 is 2n minus 3, and so all of those terms will cancel. And so all of those values cancel there, leaving me only the 2n minus 1. And so what I really have then, when I cancel everything that will tend to cancel, I have a 2n minus 1 on top. I have an x minus 4 in the numerator. I have a 2 to the minus 1 left over in the numerators. In the denominators, I have a 2 squared. I have an n plus 1. And that's all that I have in the denominators. So when I plug those values in and kind of simplify that a little bit more, what I see is that I have an x minus 4, I have a 2n minus 1, my 2 to the negative 1 I can put down in the denominator to give me an 8 with the 2 squared, and then I have an n plus 1. So if I take out the values that don't depend on x, so namely the x minus 4 and the 8, what I have is the absolute value of x minus 4 over 8 times the limit, as n goes off to infinity, of 2n minus 1 over n plus 1. Or in particular, 2 times the absolute value of x minus 4 over 8. So from my ratio test, I know that this will converge absolutely when the absolute value of x minus 4 over 8 times 2 is going to be less than 1. So in particular, that's going to tell me that I'm going to have convergence when the absolute value of x minus 4 is going to be less than 4. And so the interval on which my Taylor series expansion is valid is really going to be everything from 4, a distance of 4 to the right, so I have an 8 over there, and everything 4 to the left, so that I have 0 on that side. And so I have a radius of convergence of 4, and so I'm going to have everything in between 0 and 8 for which that series is valid. And so now if I want to talk about convergence on the entire interval, so here I would want to talk about convergence on my interval from 0 to 8, what I need to look at is then if I approximate, so if I approximate with a second degree polynomial, so basically I approximate with only 3 terms in my Taylor series expansion. So what do I have for my P2? Well, if I go back to my series expansion, I see that I have a 2 plus a 1/4 x minus 4. And then finally, for my third term, a minus 1 over 64, then x minus 4 squared. So now if I want to approximate our square root of 5 with a second degree polynomial, and I want to estimate the error bounds, I need to take a look at what Taylor's remainder theorem actually says. So in Taylor's remainder theorem, I've got a function f, and I'm evaluating that function with an nth degree Taylor polynomial. My remainder is going to be my function r sub n of x. Now, on this interval for which this series converges, or which the interval of interest, then I can actually have that remainder being a value of f to the n plus first derivative evaluated at some number c divided by n plus 1 factorial, x minus 1 to the n plus 1. And kind of where this is coming from is you can think of it as coming from either Rolle's theorem or the mean value theorem. And so kind of the punchline from that is that if I bound the n plus first derivative by some value of m, I can actually get a bound on the entire remainder for any value in my particular interval m. And so what I want to do is find this value m that bounds my n plus first derivative. So for us, what that means is we need to find a bound on the third derivative. So for our third derivative, we actually have 3/8 x to the negative 5/2 power. Now, on this interval, so remember the interval that we're interested in is our interval from 0 over to 8. And so on that interval, what happens to our function? Well, on this interval, our function is going to be decreasing. So if we look at the graph of that function, then what we can see is that if we have an interval, so wherever that interval happens to be, if we have an interval, then that function is going to be maximized then at the left endpoint. And so for whatever interval we happen to choose, the left endpoint of that interval will give us the maximum value, and that's how we find our m value for in Taylor's remainder theorem. So let's say, for instance, that for our third derivative, we had a 3/8 x to the negative 5/2, and let's say that we restrict our interval not to the entire interval that we have, but we restrict our interval to, let's keep it open, restrict our interval to 4 up to 5. So on this particular interval, if this is our I, then our maximum value for our derivative is going to occur at 4. And so if we evaluate our derivative, our third derivative at 4, we get a 3/8, and then 4 to the negative 5/2 power, which gives us 3 over 256. And so this is our value that we can take for m in Taylor's remainder theorem. So that our remainder, r of x, on this particular interval, so when we evaluate using a second degree polynomial, so our remainder on a second degree polynomial is going to be less than or equal to 3 over 256 divided by 3 factorial times our absolute value of x minus 4 raised to the third power. And so when we want to estimate at 5, so our remainder at 5 will then be less than or equal to 3 over 256 divided by 3 factorial, which is 6, times the absolute value of 5 minus 4 to the third power, or it's going to be approximately, so it will be equal to 1 over 512, which, if we kind of look at what the decimal expansion for that is going to be, then that will be approximately 0.001953. And so it looks like our approximation at 5 is going to be accurate anyway out to 2 decimal places. So if we actually try that, let's see what happens when we compare with our values on our calculator. So for the square root of 5, we have approximately 2.236067978. From our order to approximation, what we have So this one is actually from our calculator. From our order 2 approximation, we have P2 at 5, which was going to be 2, plus a 1/4 x minus 4, minus a 1 over 64 x minus 4 squared, which if we then plug in our values of 5, what we obtain then is equal to, or 143 over 64, which if we do our decimal expansion of that, what we find is we have 2.234375. And so what we'd see, we in fact do get something that's consistent, and it is accurate out to 2 decimal places, which is exactly what we expected from our remainder in our Taylor series expansion. So I hope that this has been insightful and informative, and I hope I will see you guys in the next video.